Hey guys, Greg here. I am making a new series on twisty puzzle design. I want to teach you guys how to make your own designs and hopefully see some of your designs later on. So I'm making this series where I'm going to start with simple designs. In this video it's going to be a 3x3, and then I'm going to move on to different designs, shelled mechanisms and stuff like that. So let's just begin. I'm going to be using the software SolidWorks all the time. You can get the student edition for $86 per year, if I'm not mistaken. But there's also other options. There's Onshape, which is an online solution that uses SolidWorks shortcuts, I guess, so you can do the same type of stuff. So first you're going to open a new file and save it as, because that is something you want to make sure you do every single time you make an operation. Like, you want to save, because every time you lose something, it's very disappointing. So let's just do it in the, I'm going to make a new tutorials folder. That way, alright. And I'm going to save it as 3x3. So the first thing you want to do is your shape, because before creating the parts, the individual parts, you want the final shape, because you're going to be actually cutting that into multiple parts. The final shape right now has to be a cube. So let's say you want to take the top plane and you're going to draw a cube. So a cube is obviously a square that has been extended in a third dimension. So you draw a sketch of a square, and you make sure that all the dimensions are the same, and you actually give it the size that you want. In this case, we're going to go for a 60mm 3x3. That's 6 centimeters to an edge, which is just 3 millimeters more than the classic one. And that way we're going to extend it. And to make sure that the origin, now that's a little tip for you guys, to make sure that the origin is in the center of your sketch, of your 3D sketch, you're going to do something that's called mid-plane, and that's going to extend the sketch in both directions. Let me just, I think I was a bit too fast. I'm just going to restart. So you go on the top plane and you create a sketch right here, and then you insert one of those rectangles right there. If it's going to be like a different shape, you're going to need to think about how to do that, but I will do this in another video. I'll explain that later. I'll probably make a tutorial on how to make the different shapes, the platonic solids and stuff like that. So as I said, you go to Insert, Extrude, and that's going to extend your part in both directions. So that's what you want to do. And here, as I explained earlier, you do mid-plane, and that's going to extend the sketch in both directions. Now you made the edge length 60, so you want to extend it by 60. And just press enter, and now you've got your cube. Now the mechanism for a 3x3 is a revolution, in the sense that it's something that's going to turn, as you can see, like any other Rubik's cube. So you go, okay, and that's very important, you go perpendicular to a plane, but the thing is, the origin needs to be in the center, because the core of the Rubik's cube is in the center, which is why I built the solid around the origin. So now you go into your sketch, and all you need to do is a plane that is parallel to the face, because it's going to be face turning. So if it's parallel to the face, it's going to be a straight cut, essentially. Here, you can see on a Rubik's cube, the cut is just like this, parallel to the face. Now, this is the same thing that I'm doing right now. And then you go down towards the core, and you extend it to the left. That's going to be like your hook, I guess. That's how I'm going to call it. And you create an axis of rotation, because this is the axis that is going through your face right here. This axis is going right through the center of the face, and that is the face that is going to turn. So you're essentially going to turn around this axis. Now, here, you've got this, okay, so you've got that sketch that you're going to dimension, essentially. You can I just chose 25, but it's really not important. It just needs to be smaller than, the size of the cube, essentially. So here, I put 20 millimeters. Why? Because 20 is 1/3 of the edge length, and since this is a 3x3, we're doing 1/3 to make 3 layers. So this has to be 20. This is arbitrary. I could do it anywhere along those lines, but I need to make sure it's not too short, otherwise we're going to cut the corner off, and that is not what we want. We want the corner to have a mechanism. So, right now, we're going to pick, let's say, 25, or you know what, like let's say 22. That's just out of experience. You'll learn that as you go. And here, let's say 5 millimeters. It's not necessary. 3 is enough. Let's just pick 3, whatever. And here we're gonna do a surface. So insert. Insert is like your favorite menu when you're designing a Rubik's Cube. You're gonna go to Insert, Surface, Revolve. So that's gonna take your sketch and turn it around the axis that we were building, that we were drawing earlier. And now you press Enter or OK. And as you can see, let's make the solid transparent right here. You actually have a little arrow here, and you can make a solid transparent by clicking there. You can see the sketch that became a surface. As you can see, no matter where you look at it from, it's going to be that same sketch that we just built. So a straight line that's parallel to the face, a 5 or 3 millimeter hook, and going back down to the center. So that's the core. And this is just like to make sure that the face here that we're going to cut off is going to stay in that position. So it's going to be able to turn like that, but it's not going to be able to move along this axis and that axis. So here, it's not going to be able to move that way or that way because it's a cylinder inside a cylinder, but it is going to be able to turn around the axis of rotation. And now, you want to make 6 of those. So here, you've got Insert, Pattern, Mirror, and you're going to mirror that solid that we just created, well, that surface that we created, by clicking Bodies to mirror. Click on the body, which is the surface, and mirror it along this plane right here. Now again, this is why we wanted to center the puzzle around the origin, because this plane can be used as a symmetry to copy this surface right here. Now let's just remove the transparency. And you need to make sure that these planes right there, that you have 6 of those, because a Rubik's Cube has 6 faces. So what you can do is Insert Features, Move, Copy. So you're going to move those surfaces, and here you can do a rotation. But you are going to want to keep the original one, so you make a copy, and you rotate it along the Z-axis by 90 degrees. And you'll notice that here, they are rotated around this axis right there, and therefore you actually get 4 of those. Now there's multiple ways to do this. Body Move Copy is the one I use the least. Here, if you can create an axis using 2 planes. Again, the planes go through the origin, so that's fine. As you can see, this is the axis around which I can do the rotation. And here I can do Insert, Pattern, Mirror, Circular Pattern, and that's going to copy the 2 surfaces that we've created along that axis, and you want 2 copies total with a 90-degree angle. Here's where you put in the parameters, and then you press OK, and that works too. But I do want to show you one last tip, because I won't be needing this axis. The cube has a very interesting symmetry in the sense that, as you can see from here, let's hide those, you can see this face is identical to this one and this one. It actually has a 3-fold symmetry around the corner. So what that means is we can just create an axis that goes through the corners, like that, and then do a circular pattern, except with 3 axes over a total of 360 degrees. If you put in 360, it's just going to divide 360 by the number of surfaces, but technically you could put 240 and it's going to be the same result, because it's going to do 1 every 240 divided by, well, the number of angles that you're going to have. So here you're making 2 copies extra than the first one, so it's 2 copies in total, so 240 divided by 2, 120 degrees. If you do 360, it's just going to divide the whole total by the number of copies, so it's going to work as well. And you can press OK, and that's actually going to do that copy I was talking about around the corner, that 3-fold symmetry, and now you've got all the axes down. So now, if you hide the body, you can see these surfaces that we created, and they form sort of hooks that go towards the core of the puzzle. So the core being in the center, you see that hook goes inside, so from the outside inwards, and here from the outside inwards. Same here. So now we're going to cut the body with the surfaces by using Feature, Split. And split is going to use surfaces, in this case the surfaces that we created to cut the body, and now you can see there are many parts right there, and now you have to click all parts if you want to keep them all. So I have to click 27 boxes because a Rubik's Cube has 27 theoretical parts, the core being one of those. Alright, let's just click on everything, and alright. So now we can hide the surfaces, because we've done the cutting parts. Now, when you're preparing a puzzle for 3D printing, you don't want to prepare every single piece. You want to prepare every single unique piece, because all 8 corners are identical, all 12 edges are identical. So what you're going to do is you're going to press the Features, Delete, Keep Body. Everything is in the Insert menu, by the way. So Features, Delete, Keep Body, and you're going to keep one of each individual unique parts. The core is something we're going to draw up separately. And now all that's left are the 3 unique parts. Now here's something very important in twisty puzzle design. A lot of people say, talk about spherical mechanisms. And the thing is, here it's a cylindrical mechanism, because the surface that we created at the beginning, let's just undo that. The surface that we created looks like this. And it is a cylindrical cut, because here you have a cylinder, and that's what's going to make the puzzle turn. Now there is something called the spherical mechanism, and that is something slightly different. But first I want to show you something. You see here on the edge, because of the cylindrical mechanism, the intersection of 2 cylinders is actually a sharp edge, and that's something you want to avoid at all costs on a twisty puzzle, or at least on a 3D printed design, because it makes the whole design complicated, and you cannot go into further, complications, such as the shell mechanism, for example. If you want to make more complex puzzles, you need spherical mechanisms, so you have to start with that. And the 3x3 is a great place to start. So what I'm going to do now is I'm going to switch the cylindrical mechanism into a spherical mechanism. So on the original sketch of the surface that I created right there, you can create spheres that go through the centers, circles that go through the center, because this is, after all, a 2D sketch, so it's not a sphere, it's actually a circle. And you're going to remove the cylindrical part of the mechanism. That was the hook that we created. And you're going to make sure that this is on the sphere, and instead of using a line here to make the cylindrical mechanism, you're going to use an arc, a 3-point arc. Now the 3-point arc, you select 1 point, the second point, and you click on the arc, and this is actually your spherical mechanism. It follows a cylinder going through the, a circle going through the origin, and when you revolve a circle around an axis which goes through the center of that circle, well, it becomes a sphere. So here, this is actually part of a sphere. Now we're just going to add a dimension so that it's not, so that it is actually defined. And let's just pick a diameter of 48, whatever, it doesn't really matter, as long as there's a mechanism for every single part. And just changing that, let's redo the split, because sometimes when you change stuff in the sketch, the split function doesn't really understand what just happened, and some things can go wrong. So now you're going to re-click on every single body, and it's going to recreate the bodies. And now that you've done that, you go to Body, Keep, Delete, and you're going to click on the three unique parts. And now I'm going to show you the good part of the spherical mech. As you can see, this and that is part of the same sphere, which means it's a much simpler interface between parts. And that is not something we saw earlier, because we saw that sharp edge. So that is really good. Alright, so now that I've gone through this, the mechanism portion is actually quite complete. Now there is something I'm seeing here. I'm seeing that the distance between these two faces is quite shallow, and there's a lot of room for more, a larger mechanism, because this section of mechanism right here, that's not much, and I guess we could make it more stable by putting a larger mechanism. So what I'm going to do is I'm going to go back to the sketch and see that 3 millimeters of hook size that we chose. I'm going to pump that up to 5. and that means that the mechanism here is much larger. The distance between these two faces is much larger. So that is what we're looking for. Now, I like the look of the pieces. I think that here for like the center, we're gonna need to put a cap and a screw, and between that face and this top face, there's just not much space. You see right here, not much space. And here, there's still a lot of margin because the mechanism holding the corner on to its mechanism part, which is this section right here, is actually quite big. So what we can do now is maybe add a little bit more room for the screw, because the screw is going to go here and there's not much space. So let's reduce the diameter to 44. That seems fine. And now, as you can see, we've got more space for the screw because we've got this whole section right here where we can put the screw. Now, we've done the mechanism, so the mechanism is complete. It's actually very simple for a 3x3 because it's the intersection of multiple rotations, essentially. Multiple, how do you say that? Multiple revolutions, one on each face. And as you can see, a corner, the reason why it has that shape is because it's the intersection of that spherical mechanism right here. You can see the curve that we created. Here you can see the sketch that we created right here, curving upwards and then going back down. And you see this in all 3 dimensions. Same sketch, curving upwards, going back down, and right here. Because it's the intersection of 3 times that sketch, which is really interesting, because that's what's going to keep the puzzle together. So now, we're going to prepare the parts for 3D printing. That means creating tolerances, fillets, and screw holes and everything. So, luckily for us, there are no tolerances to be put on an SLS printed puzzle. Sorry, on an FDM printed puzzle, you would need to put tolerances because FDM isn't as precise. So you'd need to add, I'd say, tolerances on the whole part. I'm not familiar enough to give you advice with certainty, but I guess around 0.1 millimeters removed on all faces. So here, if I select all the faces of the puzzle, like that, then I can do 0.1 millimeter, and I can either make it bigger, like that, or flip direction and make it smaller. And that's what you need to do with FDM. But then again, I'm not sure of the value. I don't want to, give you false advice. I'm not very familiar with FDM because I've been doing too much SLS, and so I'm not going to give you a value. But you need to, try, fail, and retry and succeed. This is the best method for anyone to learn. As for SLS, for simple puzzles like that, you do not need tolerances at all. The puzzle will adjust itself, and it will be really well printed, so you don't need to worry too much about functional tolerances. Functional tolerances are more useful for SLS when you're using V mechanisms and stuff like that, and hooks where 2 parts grinding against each other might make them lock up or just block or fuse, which is not a good thing. So for now, we have a simple mechanism, no tolerances on this one. I will explain that in another video with a more complex design, probably the 5x5. So let's isolate that corner. Alright, so now I'm gonna, wait, I went too fast. Let's right click and go to isolate. My bad. Alright, now we're going to want to insert, again, always insert, features, and you press fillet. Now these are rounded edges, essentially. So let's just take 2 millimeters. This is really arbitrary. You can pick anything, but I like to pick big fillets for the corner cuts. So essentially, when a part is going to need to corner cut at some point, the interface where it corner cuts, I like to make those fillets big. So let's just pick 3 millimeters. It's really arbitrary. But here, for example, if you have a misalignment on the 3x3 corner right there, it's going to fix itself. So that's very important. Now let's add other fillets. So this is for the outside, just the outside look. Let's just pick 1.5 and select all the outer fillets. Outer faces can work. You can either select edges or faces. If you select the face, it's going to select all the edges on that face. And finally, you've got one last one, and that's this one right here. Let's just put it at 1. The reason I don't like to make it too big is that, let's say if I put it at 3 or 4 millimeters, let's say 3, or 4, yeah, let's just say 4. Okay, it doesn't even work. 3.5. Here you've got a 3.5 millimeter fillet, and this is just not going to work because the surface that is holding the puzzle together is actually curved, so it's just going to be popping everywhere. So I like to make these relatively small, but not too small. So 1 millimeter is fine in that case. As you can see, there's still a lot of room for that hook right there. So yeah, that corner is done. So all you need to do now is to make 3D printing faster, because, well, I need to explain how 3D printing works. The SLS printer essentially cuts down your part in multiple layers, and then it's going to use a laser to solidify the layers. Well, you've got a function called features shell that's going to make your part empty. So when it cuts down the part, the laser is actually going to have much less travel time because there's less matter to fuse. So, and it doesn't really change the structure of the part. It doesn't make it any less strong. I usually make shells that are 0.8 millimeters thick. Now, just to show you one small thing, let's just redo the shell function. Feature shell right there. Here you have to select faces right here. So you just click in that box to be able to change the parameters. And here you're going to put 0.8 millimeters. That's the final thickness of your plastic. It doesn't really need to be bigger. And you select the body section right there, and you click on the body that you want to shell, and then you press enter. And that's going to make it empty. So if I do like a section cut and go through the piece, you're going to see that here it's empty, and this is the only surface that your printer is gonna need to fuse. So it's actually much faster for the 3D printer. And that's what makes 3D printing prices cheap. It's because well, the more time it takes to produce a part, the more expensive it is. And here you're using the laser's energy, etc. So the reason why 3D printing is so cheap today is because we have guidelines that we need to respect, including shelling the parts, so making them hollow. And I think that's really important that you respect that, because that's what makes the twisty puzzles relatively cheap to print. Okay, so let's undo that section view that I did. By the way, here's the section view icon. I hope I'm not going too fast. But now this part is done, completely done. So now what we're going to do is tweak the edge, prepare the edge for 3D printing. Now here's something very interesting. You can't just select that face because it has trouble identifying, like when you have two edges that intersect on the same surface, but one is like on the negative and one is on the positive on top. It's going to have trouble recognizing, so let's just insert a fillet. It's going to have trouble recognizing which edge takes over. So you see here, there's a bit of a bug in SolidWorks, and you can't really expect the machine to understand that because it's a very complex shape. So what you do in these cases, that's a very good tip to help you not have any issues with the fillets. You go to Insert, Face, Move, and you're going to select this one or these ones. It doesn't really matter, but I generally select the bottom one on both sides. And you're going to flip the direction and offset it by nothing. So by 0.001, it's not going to change the shape of the part, but at the interface, you're going to see there's a little bit of a new edge right here, and that is going to make the software understand what's going on, because he knows that this edge corresponds to the top face, this edge is on a face that's on the opposite side, I guess, right here. It's just to make the machine understand what you're doing. And now you add fillets, just like before, because as I said, there are no tolerances here. So let's just pick 3, that'll be fine. Right there. And here you've got corner cutting edges as well, so we're going to add some pretty big fillets there too. Once that is done, we're going to add the top face, the sort of visual fillets. So 1.5, and now the functional fillets on the inside that are just to avoid, parts catching between different positions on the mechanism, so different layers on the mechanism. So here you've got the outer layer and the mechanism layer. You don't want these to catch together, so you need to add fillets there. So here I'm going to add fillets everywhere. So one here, one on the opposite side, and some on the sides right there. And now, there is only one thing left, these sharp edges right there. Sharp edges are your worst nightmare as a puzzle designer, so let's just use like any fillet size. Those don't really have much influence, but you still want to remove them, so yeah, let's just remove those. And now you've got these rounded edges right there, you've got these rounded edges, these ones, the part is perfect, you just need to hollow it out. So you use the shell function, again 0.8, choose the solid, click the solid, press enter, and you've got this hollow part. Now the final part is the center. Now this part is very important. What I'm going to do is first I'm going to create the outer appearance of the part. So here, for example, I'm going to move that face right here. Now why am I moving this? I'm going to move it by 5 or, you know what, like 10 millimeters. I'm moving it backwards, that way I have more space for the arms of the core, because otherwise the core is just like a tiny cube in the center, so it's pretty pointless. The center doesn't need, technically, to have that whole stem right there. It just needs a little bit of it, so I'm just leaving more room for the core later on. Now what you're going to do at this point is, same as the other pieces, you're going to start filleting the edges. Now let's just choose 3 millimeters for those edges I was talking about that allow for corner cutting. And then you're going to be using, let's say 1.5 again for the appearance fillets, and for the rest you're going to be using something like 1 or something. It's really arbitrary, honestly. You can just pick the size that you feel like, you feel looks the best. Here, this is what my 3x3 is going to look like at the end. So I like how it looks, so it's fine with me, but if you want bigger fillets or smaller fillets, you can just choose to do that. Now, I need to prepare the center for 3D printing, but it needs to be adapted to the 3x3, and you're going to need to screw the center into the core. So now what you do is you, and by the way, to understand that whole core concept, I highly recommend you open a Rubik's Cube, remove a cap, unscrew the screw inside the center, and look inside so you can understand more visually how it works. So yeah, now I need to make a center cap, and then we're going to dig a hole inside the center for the screw to fit. So first, we need to create a center cap. So what I'm going to do is I'm going to create a surface with which I'm going to cut the cap off. So here's the axis, goes straight through the center of the part, and I've got this axis right there, which is just a line that we're going to revolve around that axis. And boom, this is your surface. Now there are other ways to do this, but I just like this one because you're essentially drawing a sketch, and you can just create a line that intersects this piece at the bottom of the fillet. So essentially you don't really see that it's a fillet afterwards. I don't know, I just like cutting it along that line right there. But you could technically select all these edges right there and do like something that's called surface planar, and it's going to create a surface that just follows those lines. You could just do this, but anyways, it's not very important. I generally do the surface revolve. If you find other methods that you want to use, feel free to use them. Alright, so now I'm going to do the same thing as earlier. I'm going to split that body right there with this surface, that body, and cut bodies. And now I have 2 bodies left, the cap and the center. I can just hide the surface now. So now I can isolate the cap. So that's what it looks like, but it needs to hold, or it needs to have a part inside that's just going to slide into the center. It's not really important what that part looks like. What I'm going to do is I'm just going to create really any part, any sort of shape. It doesn't really matter. Here I'm making a square that's 16 millimeters wide with like, let's say 1 millimeter fillets. It really doesn't matter, honestly. And right, so you can add here, you can add fillets inside a sketch. It's called a sketch fillet, so the name is pretty straightforward. And then you press OK. So now you've got your sketch, and I don't necessarily want this whole section to be extruded here. For example, I've got this, but I do want to make it hollow, because if I make it hollow, then there's space for the screw head, and that's just space you can, you can get for free. So space is very important because you don't have much space for the screw. So either you can shell that, so empty it by selecting the face this time, because earlier I showed you, you select the solid, it's going to make it hollow, but you can also select the face and it's going to make the solid hollow without the face. Okay, that doesn't work, so sometimes it doesn't work. I wish I could have shown you. Okay, let's remove that. Let me just show you what I mean by that. Here, if I shell this by selecting the face, it's going to create a shell without the face. So it's going to empty everything and remove the face in question. Anyways, there's another way to do what we want to do. Here, I've got my sketch that I just extruded. I'm going to select all those entities. So these lines and rounded edges. And I'm going to do something called offset entities. And I'm going to offset it by 1 millimeter and click reverse, so it's going to offset them towards the inside. And now if I extrude this is the shape that you get in the end. So here you've got plenty of space for a screw head inside the center, and that's a good thing. So now that the cap is done, I can just hide it. We won't need it anymore, but I do need to do the female part of the cap, because that was the male part. I need to cut the center with the sketch that I made. So now I use the sketch again. So here you can, usually when you use it in a function, it's hidden, but you can right click and press show. And now you're going to reuse it and do cut, which is, so we had boss base extrude that adds matter, and then we've got cut extrude and that removes the matter. So here I've selected the outer portion of my sketch and I'm going to reverse it, and it was 2 millimeters. I'm going to put 2.5 so that we have a margin. That's a tolerance there, so that the cap is resting on that face and not on the inner face. I want the cap to rest on that face and not that. So here I've extruded it by 2.5 millimeters. And this is the female cap, and the male cap is on top. But with 3D printing, there sometimes need to be tolerances, and here you will not be able to insert the cap straight out of the printer. You're going to need to add a slight tolerance, because here, let me just show the cap right there, and do a section view that goes straight through it. Here, it's going to be way too tight between these two parts. So you're going to need to untighten that, and to do this, you're going to press insert face offsets, face move, and you're going to click all those faces on the outside right there, and you're going to do flip direction, and you're going to move them by 0.1 millimeters, because you still want it to be slightly tight but not loose, but you still want it to be, insertable. So it needs to be 0.1. 0.2 is too loose, in my opinion, and 0 is just way too tight. You can't even push it in. So now, as you can see, there's a little bit of leeway to insert the cap right there. And that is wonderful. Alright, now that you've done this, the cap and its interface are complete. Now you need to drill a hole for the screw. Now if you do M2 screws, you need to have a diameter for the head of about 5 millimeters. Here I'm going to use M3, so I'm going to use 7 to 8 millimeters. It doesn't really matter, you're not really centering yourself around the head of the screw. You can have a little bit of leeway because the puzzle is actually going to center itself around its geometry, so it's going to be fine. So we're using a diameter of 8, and we're going to cut it down by about 3 millimeters. Now, technically, cutting this down, I created space for the screw. So technically, I would only need 3 minus the 2.5 that I've already cut out. But since we have a lot of margin, we might as well use, let's say 1 or 2, I guess 1.5 is fine. You just want the screw head to be in there and not touch the cap, that's all. So you need to have, let's just, again, show the cap and cut right through it. Okay, you need to have about 3.5 millimeters between these two faces right there, and I have 4 millimeters, so that's fine. Now that this is done, I'm going to create a hole for the screw, but I want it to be loose because the center, well, you're not screwing the center, you're screwing the center into the core. You're not putting a screw inside the center, so we're not going to need to put any tightness around the screw shaft. So M3 means that the shaft is 3 millimeters wide. So you're going to make the diameter 3.5 millimeters. That way it can just move freely around the screw. If you want to add a spring, you can do that. Just put the diameter of the spring and the depth that you want, and it'll be fine. But I don't use springs on my puzzles. So here, I'm going to go through the whole center. So here is my hole for the screw head, and here's my hole for the screw. And now my center is actually complete. So what I can do is just create a shell and make the center hollow. And now, as you can see, if you cut it down, you can see that my center is hollowed out right there. So that's perfect. So these are all my parts. I've got my center cap, my corner, and my edge. All that's left is the core. So to create the core, I'm gonna go from, let's say, that plane right there. And now I know that the origin is at the center of the core, so I'm gonna just create a circle at the center, and I'm gonna make it about 10 millimeters in diameter. Now, I need to make it less than that, but I just want to show you what it looks like when it's 10 millimeters. So here I'm gonna do a mid plane and extend it by 25 millimeters, or 30 is fine, in both directions. And I'm not going to merge the result because otherwise it's going to fuse it with the parts surrounding it. So you need to unclick the merge result. Alright, the thing is here, this is technically tangent to this face. It's honestly best to leave a little bit of leeway. That's why I was saying that 30 millimeters and 10 millimeter diameter isn't the best for the core. So here I'm going to move the face by 0.5 millimeters, so the core is actually going to be slightly smaller, and you can see there's a little bit of leeway between these two parts. Also, if the top of the shaft of the core touches the center right there, it's not going to be adjustable because the center is actually just stuck against the core and you can't tighten it anymore. So you need to move this face right here as well as this face. And let's just move them by 0.5. Now here is something you guys are going to like. Remember how at the beginning to create the surfaces, we created an axis that went through two corners, sorry, and then we did a threefold symmetry? Well, we're going to be using that axis again. Why? Because we need to make a core, and a core has it has, the same directions as the cube. Now before we do that repetition, we want to do something. So we want to create a hole for the screw inside the core. So here I'm going to hide the cap because it's bothering me. And here, since this is a plane that's right over, where the screw is, we're going to draw directly on that surface. It can be here, there, anywhere, really, but it's fine if we just create a sketch here. So I'm creating a sketch, and now I'm creating a hole that is going to be 2.7 millimeters in diameter. Now, I said it was an M3 screw, which means the outer diameter is 3. For plastic, if you put a 2.7 millimeter diameter, it's going to squeeze the screw just enough to really keep it in place. I always use the diameter minus 0.3 because that's just how it's the best in my opinion. And now I'm going to do cut, extrude, same as before. And since I use M3 times 12, essentially screws that are 12 millimeters in length, I need to make a hole that's just slightly over 12 millimeters. I can use 15 because anyways, we know that we have a lot of margin here because the core center is here. So we can even go up to 18. And as long as we just don't go all the way down to the core, let's just choose 18. 18 is fine. And now, let's see what the core looks like at this point. You've got only one arm that has a hole for the screw. And we want it to be on the other side as well because, there are 6 screws that you're going to put inside the puzzle. So what we're going to use is insert mirror. And we're going to mirror along that plane right here, this plane that is perpendicular to the current arm that we created. we're going to mirror a feature, not a body, a feature. And the feature that we're going to mirror is that hole right there. And it's going to recreate the same hole on the other side of the core arm. And now we're going to do the same as what we did in the beginning to repeat the surfaces that we used to cut the puzzle. And by doing pattern mirror, circular pattern, and we're going to click on the body, click on the axis, and we're going to repeat it 3 times around this axis. And this looks a lot like a 3x3 core, so this is perfect. And now we can just do insert, features, combine, and we're going to combine all 3 solids that are selected here. So 1, 2, 3. Press enter, and this is your core. Now, if you want to make it look a little bit better, you can also add some fillets right there on the outside, just to make it look good. You could technically even select those surfaces, and you're going to get fillets also here that look kind of cool. There was one I forgot. It's really optional, to be honest. That's not really important. I would say it's it has absolutely no importance, but I like it. It looks good. Now, one final thing. If you want to make your screw fit more easily, what you can do is in Insert Features, you can press Chamfer. And here you put a chamfer there, right there. That's 0.3 millimeters, and well, let's flip the direction. Make it 60 degrees or something. It's really optional. I'm gonna make it 70 degrees. And yeah, that's 0.5. 70 degrees and 0.5. It's completely optional, but I'm gonna explain why it makes this whole screwing process more easy. All right. Here, this is what a chamfer does. It creates like a cone in this case, so that it's easier to insert the screw inside the hole. And at the beginning, there's going to be less tension, so you're going to have much less difficulty inserting the screw inside the hole and twisting it inside that. So it's going to be easier to assemble. So now I've got a complete core, sorry, and I've got all my parts. I've got the core, the center, the cap, the edge, and the corner, and that is how I designed a 3x3. So now, just before I go, I'm going to explain how to prepare the parts for 3D printing. Now, I use a software called partstacker, where I export my STL files. So I save these as 3D printing files, and I stack them using the software. But you don't all have access to the software. I'm still going to put a link in the description below so you can get access to the software, but I'm going to explain how to do this without that software. So essentially, you want to move the parts around and copy them so that they don't touch each other. Let's say, for example, I'm going to move the center translated by 3 millimeters in the Z direction. That's really arbitrary. You just need to make sure that the parts don't touch. So for example here, then I'm going to do the same with the edge. Let's say move it 3 in the Y direction and -3 in the Z direction. And do the same with the corner, this time 2 in the Y direction, -2 in the Z direction, and -2 in the X direction. And I think that's going to be enough. I'm almost there. Just need to tweak a little bit at the positions, and here, as you can see, the corner isn't touching the edge. It's not touching here either. The edge is the edge touching the center. Here, the edge is touching the center, which means we need to move the center back a little bit more. Let's say 5 millimeters. All right. So here, the edge isn't touching the center. The corner isn't touching the edge, and the corner is definitely not touching the center. So we're good. The parts don't touch. So now we just need to repeat them around the puzzle. And now we're going to need to create axes, because we can't just repeat them manually. It's too long. So let's just create axes using the planes that we had at the beginning. So let's create axis. So reference geometry, axis. If you select 2 planes, it's already defined. Now let's do the same with all three axes by selecting 2 planes every time. As you can see, I have 3 axes, the one in the Y direction, the Z direction, and X direction. And let's just do a circular pattern where I'm going to repeat this edge in that corner around this axis and make 4 copies like that. And then I'm going to use axis 3, make another circular pattern where I'm going to select all those edges and corners that I've just created, repeat them twice around 360 degrees. So you've got, oh, I forgot the center. I need that center too. Okay. And now I just need to finish it off. So I need to make sure I'm keeping the edges and the centers like this, this, and that, this, and that. And I'm going to revolve them around this axis right here so that they are on that side and that side as well. All that's left is the center that goes here and the center that goes there. I can just pick 2 opposite centers and make a circular pattern out of those, like this. And select this axis right there. Alright, so now I've created a copy of every single part inside the Rubik's Cube, and what I can do here is File. Okay, first of all I'm going to save. I forgot to save since the beginning, but that design is actually quite easy. And File, Save As. This time you're going to save it as an STL file, and press Save. And this is the file that you're going to upload to a 3D printing company if you want to get it 3D printed. Now, I also use Materialize Magics. That's a software that creates a sort of box around your parts. Unfortunately, most companies today, if you send them this file, they're not going to print it because it's just too complex. There are too many parts, and post-processing is a lot of work. So to make it easier to post-process, they want you to make a grid around the box. Really, I'm not going to talk much about this, but let's just say, for example, I wanted a grid. I could always create a sketch with like a little square that I'm going to repeat multiple times, like that, in one direction, then multiple times in the other direction, and then create a grid by, creating like a square around it and creating this shape right here. I know it's not very well explained, but I really don't want to talk about that too much. But you see here, for example, I just created a grid. Now you just need to do this 6 times around your puzzle, and you need to put it inside a box essentially, because the companies, they want you to create a box around your model. I am going to show you what I do on Materialize, because here you can just import a part. I highly recommend that you get Materialize for this type of job. I'm not going to say how you can get it, but you guys can be creative, I guess. And now I go into SLS tutorials where I put my files, and as you can see, I've got the 3x3 file here. I can just open it, then create a scene for a specific printer, for example. And now that my part is selected, I can go in Build Preparation, Sinterbox Wizard, and that is a function that helps me make a box around my puzzle, and that is actually very useful. There is a free software to do this, another one that I use, which is called partstacker. Sorry, not partstacker. Actually, yes, it's partstacker Sinterboxer. It's a recent version of partstacker that allows you to make a Sinterbox. Again, the link is in the description below, so you can use that definitely. But just to show you, this is what, let's say this is a Lego. Alright, you can use it to make like a box around your parts, and this is what it would look like. Let's see if I can, okay. See, that's what you need to make around the parts. And once that's done, you just fuse that, merge the parts, and this is just essentially one part now that I can save as a 3x3. Replace. So now my 3x3 file is saved, and, whoops. And this is what it looks like using a viewer. But again, you can do that using partstacker, so it's going to be in the description. It's very simple to use. I'll make a video about it so that people can use it in another tutorial. For now, I just want to really concentrate on that 3x3. Once that's done, you just need to upload this file to your 3D printing provider, and they will be able to make it for you. But yeah, I just wanted to create that tutorial. That was for the 3x3. Then I'll move on to the 5x5 because it's more complex and there are going to be tolerances involved. I think it's very important, but I won't be explaining the stacking process again. Or I might make a specific video with only the stacking process. I think it could be interesting if in every tutorial I just link to the different sub-tutorials, for example, stacking or stuff like that. So it could be interesting. If you have any comments about my process, or if you have any questions, please feel free to let me know. It's a very fun project for me. I really wanted to help you guys learn how to design and create puzzles, because I think there's a lot of creativity in this community, and I really want it to be used. So yeah, this is how you create a 3x3. So I hope some people will be able to use this. And if you have any ideas or want me to make specific tutorials on how to design some specific puzzles, please let me know, and I will be making some more like those. So thanks for watching, and I will see you guys in the next video.